Okay, good morning, everyone. Thanks for well, the controls are there. So now we can hear me, right? So as I was saying before starting the plenary talk, we're gonna take 5 minutes to recognize the trajectory of two distinguished professors, Dr. Ye, Dr. Cantor. They are basically the fathers of the high entropy alloys field, and we, the Mexican Society of Materials, is really honored to present this recognition to them. And well, we are proud to have you here both. And I would ask Gerardo Cabañas, Dr. Gerardo Cabañas, to give a short bio of both. And after that, we are going to give you a present, very Mexican present, handmade present of the region. Thank you very much.
Good morning. Buenos días. Dear IMRSC participants, in 2004, the seminal papers from the groups of Professor Cantor and Professor Yi appeared in the open literature. In a recent search in Scopus, a database of papers including the terms high entropy alloys and multi-component principal element alloys, it was found that 330 papers were published on this subject in the following 5 years. This number increased to about 880 papers after 10 years. And 19 years later, in 2023, the total number reached more than 15,600 papers on the subject. And the number will likely surpass 20,000 papers in this year. It is 20 years after the publication of the first papers. High entropy alloys and multi-component principal element alloys obviously set a paradigm in the materials and metallurgy community. We used to think that more elements in an alloy would necessarily render more complex microstructures, but we were proved wrong. And this changed the game in unexpected ways, which we are barely started to explore. By a happy turn of events, Professor Yi's first presentation in an international conference on the topic of high entropy alloys occurred here at the 2005 IMRC. We thought that it was most appropriate to celebrate the landmark achievements of both Professor Cantor and Professor Yi by honoring them in this same event. Therefore, on behalf of the Mexican Materials Society, I ask you to give a standing ovation to our honorees. So, if you want to give a short few words, please go ahead.
Good noon, ladies and gentlemen. I am so moved at this moment. Sincere thanks to the President of Mexico Material Research Society and the Chair of the Congress and the organizers of High Entropy Material Symposium in honor of me. And thanks to all of you for your attendance. 19 years ago, on August 23, 2005, at this place, Cancun, I first presented my first talk on high entropy alloys to the world, invited by IMRC. Now, I come back and receive such a big honor. It's very meaningful for me to emphasize the importance of creation. Greater creation will give greater contribution and value. But it needs you to be practical and efficient to carry it out. In the long run, good mind, good creations, and the good deeds to others, the society, and the world from your young age will accumulate lots of achievements and happiness. This is true. Thanks again. Good luck to all of you. Thanks.
Well, thank you very, very much to the President of the Mexican Materials Society and the President of the Congress and the organizers of, well, all of the convention here, and in particular the symposium on high entropy materials in Professor Ye's honor. Thank you so much for inviting me too, and it's a great honor to be here. And a great pleasure to be here. I've never been to Mexico before. I've always wanted to come. I've spent a week with my wife having a vacation last week, and now I'm working for a week. Both very, very enjoyable. And the thing I can say I've discovered is Mexican people are wonderful, friendly people. So thank you so much to all of Mexican people for receiving us so well. A quick mention about high entropy materials. A couple of things to say. The first thing is, I've often said that I wish I had a wonderful theory which had predicted it, that I'd done some incredibly complicated calculations, mathematical calculations which predicted high entropy materials. Or I wish I'd had some incredibly complicated special equipment and some very special experiment which discovered them. But none of those was true. I was sitting in my office thinking about things, and I suddenly thought, why do we never find new materials by just increasing the composition of more and more alloying components? Why do we never do that? And Professor Ye has explained how he was driving his car and he had a similar thought. And I like the fact, when I think about it more now, that it's actually an entropic thought that just by happenstance occurred. And that's very suitable. Entropy led us to the idea that high entropy materials would be very good. And for millennia, people had ignored the possibility of adding more and more components. As we just heard, it was believed that this would not lead to good materials. And it proved to be wrong. So I say to everybody, don't trust what people tell you. Go and try and find out. I believe in that enormously. And I want to say one last thing about entropy. Not only is entropy good and discovery by random processes good, Professor Ye gave a presentation at the beginning of our symposium, a brief presentation, where he said something very, very important, which had not occurred to me so strongly. The peoples of this world, if they mix together, will be more entropic and will be better served than living in their own tribal camps. And I believe in that enormously as well. So I think my history of my life has been increasingly to believe in entropy in more and more different things. So once again, thank you so much, and good luck to all of you in your entropic meandering through life. Discover something exciting and have a great time. Thank you very much.
professors, on behalf of the Mexican Material Society, please receive this present. This is, as I mentioned, it's handmade from the craft from the region. And then this is Cantor Professor, thank you very much. And this Professor G, thank you very much for coming. And congratulations for your great job in this field of
Good morning, ladies and gentlemen. It is a great honor for me to introduce Professor Thomas Schrefl, an Austrian scientist who is currently head of the Center for Modeling and Simulation at the Danube University Krems and leads research of the Doppler Research Laboratory for Magnetic Design in collaboration with Toyota. He has also held professorship positions at St. Pölten University, Vienna University of Technology in Austria, and the University of Sheffield in the UK. His research interests include micromagnetic simulation, intelligent materials, nanosensors, and high-frequency oscillators. He has participated as leader research in many projects related to applied magnetism, such as complex magnets for advanced energy applications, magnetic design through physics-informed machine learning, nanostructure, multi-phase permanent magnets, among many others. His topics of research emphasizes the importance of applied material science for industrial development, showing magnetic materials as a technologically relevant type of materials. So, Professor, thank you very much for your contribution to this conference. Thank you.
So, thank you very much for the introduction. It's a real pleasure to be here. Welcome, everybody. This will be a talk about magnets and also the use of artificial intelligence in material science. So, before I start, I'd like to acknowledge the people who contributed to this work. So it's people of my group in Austria, but it's also researchers from Toyota Motor Corporation. I also have to acknowledge people from AIST in Japan and from the Institute of Solid-State Physics at the University of Tokyo. They provided us with ab initio simulation of intrinsic magnetic properties to increase our database for machine learning. So what you see here are the green sea turtles, and if you go along the coast from Cancun south to Tulum, you will have the chance to meet these very nice creatures in the sea. And the sea turtle are very fascinating animals because they use a magnetic map for navigation. They not only can orient, like we do sometimes with a compass, to find a certain direction, but also they have an imprint of the magnetic field map on the Earth. The magnetic field on the Earth has an inclination and a field strength, and both inclination and field strength, with this you can locate exactly where you are on Earth. And the sea turtles, after they are born, they swim out into the sea, and maybe after 10 years, they come back exactly to the place where they have been born. And this is due to their magnetic navigation possibility. How does this work? How did they learn to do this magnetic navigation? So this is all based on evolution, genetic modification. And evolution has two important processes. One is natural selection, and the other one is mixing of genes. And what we can do nowadays with our computers, we can try to reassemble this process of natural selection and mixing of genes in order to solve problems. And what we can do in material science, we can use genetic algorithm in order to optimize our materials. If we think about Mexico, and it's nice for me to be here in this country, it has a long tradition on magnetism. So one example is this carved stone found 300 before Christ in Chiapa. And what's very interesting, this turtle head is magnetic. So all the magnetic field lines concentrate towards the mouth. And this tells us that the people living in Itzapa had a knowledge about sea turtle navigation, because all the other stones and rocks and also sculptures found at this site, they didn't have like a magnetic imprint in the stone. So the people knew how to process materials and make magnets on a purpose. And maybe even the first permanent magnet made by humans in the world was done in Mexico. So this artifact here, which was polished and had this groove in here, was probably the first permanent magnet. It dates back to 1,000 years before Christ, and it was found in San Lorenzo. It is hematite with some lamella of iron titanium oxide in it. And most likely, it was also used as a compass. So just to let you know, this was the site where this magnetic turtle head was found. This was the site where the first permanent magnet by human beings in the world was found, and I'm glad to be here and to tell you now about magnet design with artificial intelligence. So here's the outline of my talk. First, I'd like to tell you a little bit about permanent magnets, their current use, and the future demands for permanent magnets. I will talk a little bit on inverse design, how we can use machine learning and genetic algorithm to guide our research towards the properties we want to have in the magnet. Then I'd like to give you two examples, one on neodymium substituted permanent magnets. We know most prominent permanent magnets nowadays contain neodymium, and we want to replace neodymium by more abundant elements. And finally, I will give you an example of generative deep learning in order to find optimal structures, granular structures of permanent magnet. What you can see on the left is the rotor of the motor of a car. And you have this soft magnet, and there are these slits here, and in the slits, there are these permanent magnets put in. And the main problem we face in mostly every application of permanent magnets is that we have a certain operating temperature. And unfortunately, in most magnetic material, the hotter it gets, the more they lose their strength. And we don't want to have magnets that become demagnetized during operation. So we are searching for certain chemical compositions that give strong magnets even in the operating environment of the magnet. So let's come to the modern history of permanent magnets. So these are the permanent magnets, how they developed over the last 100 years. On the y-axis here, we have the energy density of the magnet. The energy density is the energy stored in the field that is produced by the magnet. So this means this is really the energy that we can reversibly use in a magnetic device, in a motor. We see it all started off with steels and alnico magnets with a low energy product. Then, like at the 70s, the samarium cobalt magnet came in, and then in the 80s of last century, the neodymium iron boron magnet was invented, and this is really the magnet with the highest energy product nowadays, and therefore it is used in most applications where we need strong magnets. How do we measure the properties of the magnet, and what are the most important properties of a magnet? So normally you measure the properties of a magnet by putting the sample into an electromagnet. The electromagnet creates a field, and the magnet responds with a magnetic induction or magnetic flux. And this magnetic induction is measured by these measuring coils around the magnetic sample. So if we do the measurement, then we can plot the magnetic induction as a function of the magnetic fields. You can see a typical ideal hysteresis curve here. We see that magnets have hysteresis, so if I apply field, the magnetic flux increases. Then if we reduce the field, the flux goes down. At a certain point, we reach zero magnetic flux. This is a so-called coercive field. And then we go down and reverse the field, and we have the typical hysteresis loop of a permanent magnet. In addition to the coercive field, other two important properties are the remanent magnetization. So this is the magnetic flux that remains if there is no field applied in the magnet. This is an important quantity because this is related to the field that is created by the magnet itself. And then the largest rectangle I can put below this curve is the energy product. So let's have a look at the three properties again. So we have the remanence, and the remanence is proportional to the field created by the magnet. So very important, high remanence gives us a high field that the magnet can create. Then we have the coercive field. The coercive field is the resistance to demagnetization. A magnet is always exposed to a magnetic field in application. And what we want to avoid is that the magnet becomes demagnetized. And if we do simulations, we see that all the magnetic moments point up, indicated by the red color, but at certain points, if the external field is strong enough, the magnet can become demagnetized. As you can see here, it's typically happening at edges, corners, and grain boundary faces. The third important property is the energy product. This is proportional to the energy stored in the field of the air gap of a magnetic device. And now what we want to do is we want to find magnets with certain given properties like a certain remanence, a certain coercive field, or a given energy product. Now, before we go into details of how this can be done, let's have a quick look at the total neodymium iron boron market. So we see that most neodymium iron boron magnets go into direct drive wind turbines. This is about 40,000 tons per year. The next big sector is hybrid and electric cars. Then we have electric bicycles. Then are magnets in industry and commercial motors. Then we have the automotive sector. So this is like the normal combustion engine motor. But in the car, there is not only the motor, but there are many, many magnets which are used. So this is also a big portion. Then still, there's a lot of magnets going into hard disk drive and also in acoustic transducers that we have in our cell phones or earbuds. But these are tiny magnets, but they still make a big portion of the total usage per year. Neodymium is available in many countries, but if we see how much future protection we will have, we will see at least these are numbers for the European Union. So because of the growing need for magnets in wind turbines and for the growing need of magnets in electrification of transport, there will be a demand of rare earth metals that is 6 to 7 times higher than now by the year 2050. So we need to do something about it to match like demand and supply of critical raw materials. What we can do is we can design new materials. And when I was a student at Vienna several years ago, we did this traditional design of materials. So we started with processing the materials, we did some measurement, we had tables of the measured magnetic properties, we did some imaging in the electron microscope, and we also did some simulations in order to understand the relation of the properties, and then this whole cycle started over and over again. Nowadays, with the help of artificial intelligence and machine learning, we can do inverse design. So the idea is that we start with the desired properties, and then clever computational algorithms gives us the chemical composition and the structure of the magnet needed so that we will get our desired properties. And in the following, I will tell you how we go towards this inverse design in magnetic materials. One important ingredient in inverse design and the use of artificial intelligence is the amount of available data. And one way to produce data is to do simulations. Simulations are good because they are cheaper than doing like expensive experiments, and we can run a lot of simulations to generate data. And what we do in particular for magnet design is finite element micromagnetic simulation. What does this mean? So we do finite element simulation like we know from finite element simulation of structural mechanics or finite element simulation of electromagnetic devices. But we do this finite element simulation on the scale of the microstructure of the materials. So we create a synthetic microstructure, we create a finite element mesh of this synthetic microstructure, and we calculate these hysteresis loops that I have shown before. So how do we do so? We subdivide the grains and the grain boundary phase into finite elements. We interpolate the magnetization vector and the magnetic scalar potential on this finite element grid. And then we minimize the total energy of the system for varying applied field, and we get the demagnetization curve. If we talk about magnets, we immediately see that we have to understand the properties at very different length scales. On the very left, we have the atomic structure of the materials. So for example, if we go to neodymium iron boron, we have 128 atoms in the unit cell, and we know the arrangement of the atoms. And then this main neodymium iron boron phase is located next to a grain boundary phase with certain properties. And the atomic arrangement of the material and the atomic chemical composition determines the magnetization and the magnetocrystalline anisotropy of the material. Magnetization is important because the higher the magnetization, the stronger will be the field the magnet produces. The anisotropy is important because the higher the magnetocrystalline anisotropy, the stronger will be the magnet against an external field. If we look at the microstructure at the scale of grain boundaries, we see that different boundary phases can occur, and these different boundary phases most of the time act as a defect, so they reduce the coercive field of the permanent magnet. And we have to understand these properties of the defect either by ab initio simulations or by magnetic measurements. If we go up in length scales, we have the granular structure of the material, we have the grain size, we have different phases, we have the structure, and we have a knowledge of them by X-ray diffraction measurements or scanning electron microscopy. And then finally, we go to the device level where these magnets are in the rotor of like a motor. Here again, we have some design opportunities we can invest by finite element simulation of the device properties. But now, if we want to optimize the material at a certain length scale, we also need the information from the smaller length scale. But this is not readily available because we need to do ab initio simulations or measurement. And so in order to make this information from the lower scale readily available for optimization on the larger scale, we need to do machine learning surrogate models that, for example, give us the intrinsic magnetic properties when I give the chemical composition as input, that will give us the local coercive field if I give the granular structure as an input, or which tells me how all these grains will reverse if I give the grain structure as an input. So we use machine learning models in order to bridge the different length scales involved in a magnetic device. Talking about machine learning and artificial intelligence in material science is a little bit different from what we know nowadays with ChatGPT, large language models, big data. We normally don't have big data in material science. We have a few experiments, we have a few simulations, but we don't have millions of data sets. So we need to be clever in how we choose our machine learning models. One way we found very useful is to go back to very classical methods like principal component analysis or partial least squares. So this is a way for feature reduction or dimensionality reduction. So instead of many variables, we break it down to only a few variables that contain the same information. We use neural networks, but not very big neural networks. It's very small neural networks that relate input to output. And finally, I already mentioned it, we use genetic algorithms in order to optimize materials. The nice thing about genetic algorithms is that we can do multi-objective optimization. So we have, for example, two objectives, and from generation to generation, we can see how the material evolves, and from generation to generation, we just mimic or resemble what's going on in natural evolution by selection of the best individuals in the population and by mixing the properties, mixing the genes. I'd like to give you now a few examples. The first example is on neodymium iron-boron-based magnets, but neodymium is expensive, and so we want to replace this maybe with other materials like cerium and lanthanum. We might want to include a little bit of cobalt to increase the temperature stability of the magnet. But we know that having a magnet that might contain only cerium and lanthanum and no neodymium and dysprosium or praseodymium, the magnetic properties will be very poor. So one way is to use two-phase materials using core shell grains, where we have a grain where in the core there is a lot of lanthanum and cerium, and in the shell we have a lot of neodymium. And by having a clever combination of different phases in the core and the shell, we can reduce the neodymium and still have very good magnetic properties. And here machine learning comes into play in order to find like good combinations of these materials. So let's come to the design questions we have. So here on the left-hand side, we have the design goals. So our first design goal is we want to have a magnet with a certain magnetization and a certain magnetocrystalline anisotropy at a given temperature. Remember, the magnetization is related to the strength of the magnetic field produced by the magnet, and the magnetocrystalline anisotropy is related to the material's resistance against demagnetization. And now the question is, how do we choose the chemical composition in order to get like a certain range of intrinsic magnetic properties? The other question would be, if I not only look at the material, but I put the material in a magnet like this core shell granular structure, what would be the best chemical composition in the core, in the shell? What would be the best geometry for the core size and the shell thickness in order to minimize the price of my material and to maximize the coercive field? So one thing we always have to do is we have to gather all the data we have. In our case, we had magnetic measurements, like given a chemical composition, measured at a certain temperature, we have the anisotropy fields and the magnetization measured. We realized that we can do much better predictions if we augment our experimental data with a data set coming from first principle simulations. In the first principle simulations, our friends at Tokyo University can compute the magnetization, the lattice constant, local magnetic moments, exchange integrals. There's a lot of data that could be provided by the simulations. We use all this data that you see on the left-hand block in a machine learning model to predict anisotropy and magnetization. Here you can see how this machine learning predictor performs. So what we plot here, for example, on this side is the predicted anisotropy constant versus the experimentally measured anisotropy constant. If you do this machine learning, you always make a kind of a test. So you put away a fraction of your data, the so-called test set, and then you check on the test set how well your predictor will predict the anisotropy constant, for example. And you see that the prediction is quite the same on the test set as well as on the training data that was used to train the machine learning model. And you see we have this almost straight line, and the mean absolute error is less than 10% of the absolute value. We can do the same with saturation magnetization. Again, we have the plot of the predicted saturation magnetization against the experimentally measured saturation magnetization. Okay, now we already have a tool to play around, so we can go to the computer and say, okay, what will happen with my intrinsic magnetic properties if I change my chemical composition? For example, if I go from neodymium iron boron and then start to replace neodymium with lanthanum, how will the anisotropy constant change at certain temperatures? And this you can see on the left-hand side. So we see how the anisotropy changes if I change the chemical composition. We can do the same with the saturation magnetization. This is useful because, like, engineers can now play around, put in a chemical composition and see what is the expected anisotropy or magnetization. But we can do much more. We can help to understand why we observe a certain property by use of machine learning. So we can interpret the predicted values. So for example, we look at a certain chemical composition, neodymium O4, lanthanum O6, then iron O6, cobalt O4, and boron. We see this composition has a certain magnetization of 1.32 Tesla. By using the machine learning analysis, we know from in all our data set, the mean magnetization is at this value here. Because we don't have any cerium here, we increase the magnetization. We are at a higher temperature. We predict at 433 Kelvin. Because we are at elevated temperature, we reduce the magnetization. Because we have a certain amount of cobalt, we increase the magnetization. And because we have lanthanum instead of neodymium, we decrease the magnetization and become to our predicted value. What we learn from this analysis of the local contribution of the individual elements is that the reduction of magnetization by lanthanum can be compensated with the cobalt content. Now we can also do inverse design. So our question is, what are possible compositions if I want to have a certain anisotropy and a certain magnetization? We have our training data. We have the machine learning model I have just presented. And now we can do multi-objective optimization using a genetic algorithm. And the two objectives are having a certain anisotropy and having a certain magnetization. The nice thing here is in the genetic algorithm that we have the machine learning model to calculate the objective function. In genetic algorithms, we have to do many evaluations of the objective functions, and the machine learning predictor is very fast. So here's an example. So we have this tool set where we ask for a certain temperature. We want to have at a certain temperature a certain magnetization, and we want to have a certain anisotropy constant. And then we get as output a certain point with a certain chemical composition and the predicted anisotropy value and magnetization value for this certain point. And you see, we find new chemical compositions that hasn't been already in our data set. Now, if you want to make a magnet, it's not only important to have a good material with good intrinsic magnetic properties, you also need a proper microstructure of the material. And remember, before I was talking about this core shell structure, where we have a core with less neodymium and a shell maybe with high neodymium. But the question now is, what are the proper phases for proper chemical compositions for the core and the shell? What are the best sizes for the core and the shell? And what we can do the very same. We can generate a lot of data and then do inverse modeling. So we generated a lot of hysteresis curves by varying the chemical compositions of core and shell, and also the size and shape of the grains and the thicknesses here. And we did so with a very small neural network. Now we have to bridge the length scales. So we have the length scale of the unit cell, the chemical composition, towards the intrinsic magnetic properties, so shown by these two boxes here. And then we have the length scales of the granular structure of the magnetic material. So we now have our physics simulator that computes the coercive field. We do a lot of simulations. We generate training data. This training data is used for a neural network predictor of the coercive field. This neural network gives us a very quick estimation of the coercive field, and because it's so fast, we can use it in a genetic algorithm to find the best solution. What we wanted to do is we wanted to see what would be a proper composition of the shell and the core. So what is a good chemical composition, and what are the good geometric quantities in order to minimize the price and to maximize the coercive field of a permanent magnet. So in this plot here, on the one axis, you see the price in Japanese yen per cubic centimeter, and on the other axis, you see the coercive field, and the points here are the Pareto front of the best solutions. And the color code gives you the neodymium and praseodymium content of the shell and the core. You see, for example, if we pick one solution here, we have a certain neodymium concentration of 0.22 in the core, and in the shell, in order to make it more strong, we have much more praseodymium than in the core. Again, we can use the machine learning model to tell us a little bit on why this magnet here has a certain coercive field. So we can look at the different contributions to the coercive field. So a very positive contribution is that the intrinsic average switching field of the two phases is very high. A positive contribution is that the magnetocrystalline anisotropy of the shell is very high. We have a negative contribution. We assumed, as it occurs in real magnets, that there is a soft magnetic grain boundary phase. It's positive that this grain boundary phase is smaller than the nanometer, and it's negative that it has a high magnetization. But for each of these points here, we can see what are the different factors that contribute to the coercive field of the magnet. With genetic algorithms, we find new unexpected solutions. And one of the new unexpected solutions, for example, here, was that we also have a prediction where the genetic algorithm says, okay, you can also do the other way around. You can have a high neodymium concentration in the core and a low neodymium concentration in the shell. Now let's come to a very different topic. So we were already talking a little bit about microstructure of the material. And we all know we can do microstructure images by scanning electron microscopy, for example. And if we maybe learn from artificial intelligence or artificial intelligence that is used for image processing in other parts of the society, maybe we can use these methods also to improve the structure of our magnet. So what you can see here are images of people, but the very interesting thing is that these persons do not exist. So these images that you see here are created from random numbers in a latent space. So you can go to this website, and whenever you go to this website, you get an image from a random person that doesn't exist. But the cool trick here is that all the information needed for these faces are encoded in a low-dimensional space. So here's an example that depicts this low-dimensional space. So we have two persons here, a female person, a male person, and these points here represent other persons in this latent space. A space has a certain meaning. So if we want to go from Cancun to Tulum, we know which direction we want to go. Similar, in the space of images, there is a direction which points from male to female. There is also a direction that makes you smile or not smile. And then what you can do is you can play around with vector arithmetic in this Latin space. You can have an original person, and you can add a smile vector to the person, and then you have a smiley lady. You can have image of a male. You can add a female vector, and you change the expression of the face. So what you know from this artificial intelligence with images, that we can manipulate the properties if we understand this Latin space where the images are encoded. So now let's do the same for images of magnets. In order to get a lot of images of magnets, we generated artificial microstructures. And in these microstructure images, we have this color code, and this color code just gives us the orientation of the crystallites. So like blue is crystallite to the left, and red is crystallite to the right. And what we now do is we try to learn a latent code, so a code that represents the granular structure. And we do so with a deep neural network, and this deep neural network does nothing else like it tries to produce the same output from the input, but in between there are only 512 neurons as opposed to 25,000 pixels in the original image of the structure. So with this, we can encode microstructures of our magnet. Once we have encoded the microstructure of our magnet, we can compute the demagnetization curve because we know the structure, and then we can use the code and learn the demagnetization curve. So we have a neural network that gives us, if we give this code of the granular structure as input, we get the demagnetization curve. Now we can predict demagnetization curves. So you give me an image of a microstructure, I encode it into a low-dimensional lattice code. We have a predictor that predicts the demagnetization curve from the lattice code. And does it really work? Yes, it works perfectly. So here we have grain structures generated on the computer. In blue, we have the associated computed demagnetization curve. And in orange, we see the prediction of our machine learning model. Now we can also do inverse design. So we have a certain code. Let's call it X. This code represents the granular structure of a magnet. We put the code into a neural network, and the neural network gives us the hysteresis curve. So we have a mathematical function where we put the code, and the output is our hysteresis curve. Because we have this algebraic relation between the latent code and the hysteresis code, we now can do a simple minimization task. So we want to minimize the predicted hysteresis for a certain latent code minus the hysteresis properties for like a certain target magnet. And if we minimize this difference, we get the latent code for a given demagnetization curve. So the idea is now that I have as input a certain demagnetization curve, I get as output the latent code of my granular structure, and because I have a one-to-one relation between the latent code and the granular structure, I now have an inverse design that, given an input for a certain demagnetization curve, I get a microstructure that, if I'm able to realize this structure, will exactly create this demagnetization curve. So here are two examples. So this is one magnet with a very square hysteresis loop, and we get this microstructure where all the grains are almost perfectly aligned. Then we have as input this slope with a very steep slope, and we get as microstructure a magnet where we have much more misalignment. Now we have to relate this to experimental data. So we have a lot of scanning electron microscopy images, and we can create equivalent 3D microstructure models. For the 3D microstructure models, we can compute the coercive field. And here, for example, you see how the coercive field changes with the grain size for microstructure models that resembled sintered neodymium iron boron magnets. So we also can learn and see how the magnetization will switch throughout the application of an external field. So if we apply an external field, we see that we form this avalanche of reversed grains in the magnet. So what we propose to do now is we generate training data, and we can generate image-based training data not only on simulation, but we can make relation to experiments by doing micromagnetic simulations that resemble real microstructures. And then we can tune and change this artificially synthetic microstructure and, for example, change the grain size or change the aspect ratio of the grains. If we collect a lot of data, measured data and computed data, we can feed this in a neural network, and then we can use this neural network as a surrogate model for optimization to create magnets according to our wishes, our design. With this, I'd like to summarize. So I have shown you that we can use surrogate models for coercivity. We can use this, for example, to minimize the price and maximize the performance of a magnet. We get the required chemical composition and also the required structural properties of the magnet. And we can do a lot with images. We can do image-based prediction and optimization, and therefore have a handle to further optimize magnets for the future. Thank you for your attention.
I have a question about the inverse design. So you propose the desired magnetic properties, and using artificial intelligence, you find the materials that will give you that particular property. But what about that particular combination gives you a very brittle material or a very soft material? Or so what about how do you balance the other properties you need in the permanent magnet, besides the magnetic properties?
Okay, yeah. So as I understand, the question is also related to, say, mechanical properties in addition to the magnetic properties. So for now, we don't take them into account, but I think it will be possible also to include some additional properties, not only magnetic properties, but then we also need to predict and look at like the hardness of the material. But I think this is theoretically possible. What I know from people in motor design is that the mechanical properties, at least for the moment, are not of such a high importance.
Hello, thank you very much, Doctor. One question. In terms of comparing the regular method for material designing and the one using AI and everything you're explaining to us, like what is the difference in time and also in the difficulty of applying this method? I mean, do you really save like a lot of time, or is it the same, or is just that it's more accurate? And also if it's more difficult, or is it the same? I don't know, something like that, please. Thank you very much.
Okay, so I guess one bottleneck in the method I presented is that you need data to train your machine learning models. And I guess a common practice could be that whenever we do simulations now, we do measurements, we put this into a database. But once you have your data sets, then it's easy and fast to do your predictions. For me, after like, say, an effort to create the data, you can immediately have an answer. Whereas if you do a computer simulation or you do an experiment, it takes a lot of time as compared to the machine learning answer. But the critical thing is collecting all the data in advance.
But you will need like a supercomputer. I mean, in Japan, they have, I think, it's one of the best ones they have in the world. So
you don't need a supercomputer for what we do here, because we don't have much data. So we have data sets, you have seen it was about 1,000 data points. So this can be done like on workstations you have maybe in your working group. So it's very different from AI, what we know from Google and all these big data companies. So we have small data sets, and therefore we only need small computers to do our work.
Thank you, Doctor, for your presentation. My question is about the image. What kind of resolution do you need to encode this image and predict the magnetic properties or behavior of the sample that we are looking for?
Okay, yeah. So it depends a little bit on here. So the resolution here is maybe 512 times 512 pixel in this image here.
My question was because sometimes when we are watching an image on a microscope, the interaction between the electrons and the samples making like look something that is not focused. So that's why my question for the resolution. You need a very good resolution, or it could be whatever?
It's probably not so important. So what we do, for example, the scanning electron micrographs you see here. So we have maybe one magnet, and we make 10 slices, and then because of we average more or less, or we do some statistics over more than one image, the individual image is not so important. So it's statistical properties of many images which are important.
Thank you, Thomas, for the talk. It's very interesting and very impressive how can you use these kind of tools to predict properties of materials. My question is related to the other ones. I guess those methods are not independent to each other. Since, for instance, taking or watching at this slide, this image-based production is based on a big number of microstructures, right? That are also correlated to magnetic properties of the material, right?
Yes, yeah.
So, and just like this, can you use the prediction not only of these functional properties, but also mechanical or thermal stability or no, whatever? Is that?
I think in principle it's possible. So what we have here in like what it's called here measured and computing data, I have like an image and I have the equivalent magnetic data. So in our lab we also did a similar project, but it was only focused on hard metals, on the mechanical strength. So if we have measured data of images and then the mechanical properties, I hope and I know that we can do a very similar process.
And now the question is, how big is the data set you expect to have? So the minimum size of the data set to hope for having good prediction by using this methodology?
Okay, so here we worked with data sets of around 1,000 samples. And it worked well. So in different projects, we started with even less. So that's
means that for a specific material, so what it is already reported in a well-known material in the literature can be good enough if we will have a database for doing predictions.
Yes, so what we did also is we started, before we had our own data, just with scanning the literature.
Okay. Okay.
Thank you for your talk, Professor. I want to know if there is a website or a GitHub site where there is data sets freely available. Because, you know, as you said, the main trouble or one of the main troubles is to start with data, and sometimes it's not available. So I want to know if in your experience you have collected this data, or is there a place, or I don't know, with direct communication for someone who wants to start training in these kind of techniques?
I think there's this material databases like Materials Project, Nomad, Quantum Materials, a few materials databases available that you can do. For properties like mechanical properties, hysteresis properties, I didn't find a lot of databases. So we were really doing manual work on taking it out of literature. Nowadays, I guess there are some machine learning tools that help you a little bit to take out data from papers, but it's really an open problem you are addressing. So there is not any commonly available data sets that are really useful for advanced properties.
Okay, thank you very much.
Yes, I was intrigued by your core shell structures, and I can understand how you could predict if you manipulated the concentrations of the core and the shell, what the properties might be, but is there any element in your approach that can tell you whether you can actually generate that through a particular processing approach? It is not trivial because you need to know, diffusivity, equilibrium segregation, and things like that. So what's involved in that?
Yeah, that's a very good question. So let's maybe go to this slide here. So indeed, we make a prediction and we don't tell how you can produce it. What we know, for example, in this case, the core shell structures are obtained by grain boundary diffusion. So you start with a material that only has like the cerium containing grains without neodymium, and then you put neodymium copper on the surface and let it diffuse. And there is a lot of data already also on this parameter, on this diffusion process. But we haven't matched these two things together now that we also know what processing properties I need to get like a certain.
Presumably you have tools. I mean, if you are going to diffuse through the grain boundaries, say the shell material, you need to know something about, you need to do it at higher temperature, presumably, and you need to know what the diffusion behavior is and how the elements might distribute and why they're not going to the grains instead of staying at the boundary and all that. So are there, is it part of your set of algorithms that you have information on diffusivities, on equilibrium concentrations and things like that?
So currently it's not part of the algorithm. So here we rely on the experience of the people who do the corresponding experiments. I think in this diffused magnets, so they are commercially used now. So I think this process of grain boundary diffusion in permanent magnets, at least for some people, is well understood.
Okay, thank you. Just one last question. Can you introduce, for instance, the modeling of the domain wall movements, thinking in soft magnetic properties, prediction of soft magnetic properties?
We can do so, yeah, but its soft magnetic properties are a little bit more complicated because we really need to understand like the motion, maybe also eddy currents.
That is feasible.
Yeah, it's feasible, yes.
All right. Well, thank you very much. We can please give an applause to Professor Schrefl. Thank you very much.
Well, on behalf of the
Please stay just for a second.
chaos, just on behalf of the Mexican Material Society, we want to give you this acknowledge.
Okay, thank you very much.
And also this handcraft.
Okay, thank you.
Thanks to you.
Thank you.